Hello, welcome to part 2 of 2.5, which is implicit differentiation. We're going to keep going with it. And then we're also going to talk about logarithmic differentiation. So first, with the implicit differentiation, so you remember this is when we try to take derivatives of equations where there's x's and y's on the same side of the equation, and then this is when we need to use our y prime. Okay. So what I want to do with the continued version is now to find the second derivative of using implicit differentiation. So if you remember the first derivative, easy. You just make sure you remember to use y prime. Second derivative, slightly more involved. So the example I'm going to use for today is x squared plus y squared equals 25 as my equation. And we are trying to find the second derivative. So first of all, you've seen like dy over dx before. That just means the first derivative. To find the second derivative, this is the way that we write it in that format. So it's like d squared y over dx squared. I don't have a good answer to why it's written like that way. But if you ever see this, it just means to find the second derivative. Okay, so we're going to find the first derivative first, and then use that to find the derivative again. And that'll be our second derivative. So starting with the first derivative, using implicit differentiation, we know the derivative of x squared is just 2x. The derivative of y squared is just 2y, but then we have to multiply it by y prime because we're now taking derivatives of y's instead of x's. And the derivative of 25 is just 0. Okay, not too bad. But remember, our goal was to get y prime by itself, so I've got to move some stuff around. So I'm going to subtract 2x on both sides, and then divide both sides by 2y. That way I'll get y prime by itself. So simplifying that out, I end up with the first derivative of negative x over y. Okay, so continuing from there, finding the derivative of this equation that I just got will give me the second derivative. So on the left side, if I'm looking for the second derivative, this will just be y double prime now. On the right side, I have negative x over y, which means I'm going to need the quotient rule because I have stuff that's being divided. So I'll stick the negative with the x. You can only put it either on top or on bottom. You can choose. I'm just going to go with the top. So the derivative of negative x will be negative 1. The derivative of y will be 1 y prime. So remember, we still are taking derivatives of y, so we still need the y primes. Okay, then using our quotient rule, low d high minus high d low all over low low. So low d high minus high d low all over low, low. Gives me y times negative 1 minus negative x times y prime all over y squared. Okay, I'm just going to simplify this out. Remember, our goal is to get y double prime by itself because we're looking for the second derivative. The only thing is I also don't want that y prime there because this y prime right here, we actually know what y prime equals. We have that y prime equals negative x over y, so we can actually plug that in for that. So when I simplify here, then it's a little bit easier because y times negative 1 is just negative y minus negative x times negative x over y. When I substitute in the y prime, will make it slightly easier to deal with. So simplifying this from some more, I end up with negative y minus x squared over y on top divided by y squared. So because I have complex fractions, I'm just going to multiply everything by the common denominator of y. So we'll multiply the top and the bottom by y over y. And this will give me negative y squared minus x squared all over y cubed now. This looks much nicer. Okay, we're almost there. I just want to simplify just a little bit more because if you remember, our original equation was that x squared plus y squared equals 25. So on top here, it kind of looks like an x squared plus y squared if I factored out a -1. That'll make both of my x squared and y squared terms positive. And then I can substitute in the 25 for the x squared plus y squared. So my final answer for my second derivative is that it's going to be -25 over y cubed. Kind of crazy how simple the final answer looks compared to when we first started. Alright, so I want to do another example like this with you just to make sure we really got this down. So this time my equation is going to be x minus 5 squared plus y squared equals 36. And again, we're finding the second derivative. So start off by finding the first derivative. So with this x minus 5 squared, we're going to need chain rule because we've got an inside and outside. The inside is x minus 5, the outside is the stuff squared. So the derivative using chain rule is going to be the derivative of the outside. So using power rule, it's going to be 2 times x minus 5 times the derivative of the inside. The derivative of the inside of x minus 5 is just 1. And then because we're taking derivatives of x's, we don't need that y prime thing. Okay, then we have the plus y squared. The derivative of y squared is just 2y, but because it's a y, we'll need the y prime. And then the derivative of 36 is 0. So then remember we're trying to get y prime by itself. So I'm just going to subtract the 2 times the x minus 5 over to the other side. So if I distribute out the 2, it'll end up being 2x minus 10, and then subtracting that onto the other side will give me negative 2x plus 10, and then I can just divide both sides by 2y to get y prime by itself. Okay, so that's my first derivative. So for my first derivative, I'm actually going to simplify this just a little bit more because I see that everything divides by 2. So my first derivative is going to end up being negative x plus 5 over y. Okay, so now we can start finding the second derivative. I'm going to need the quotient rule because I've got a fraction. So on top, negative x plus 5, the derivative is going to be -1. On the bottom, the derivative of y is just 1, but because it's a y variable, we'll need the y prime. So 1 times y prime is just y prime. Okay, quotient rule. So low d high minus high d low all over low low. So from here I want to simplify this out and also plug in y prime because I know y prime equals negative x plus 5 over y. So this will end up being y times -1 is negative y minus negative x plus 5 times, and then instead of y prime, we're going to plug in negative x plus 5 over y in the place of y prime, all over y squared. Okay, so continuing onwards, we have negative y minus, I'll write it as negative x plus 5 squared over y, all over y squared. And again, complex fraction, so we're going to multiply the top and the bottom by y, so that we can get rid of our complex fractions. Okay, so multiplying by y, I end up with negative y squared minus negative x plus 5 squared, all over y squared. Okay, and on top, it's kind of like our original problem again. So if you remember, our original problem said x minus 5 squared plus y squared equals 36. So I also want to look at my negative x plus 5 squared right now, because if I have negative x plus 5 squared, it almost looks like x minus 5 squared, but not quite, because there's things that are negative when they should be positive and so on. So if I factor out a -1 out of my negative x plus 5, this will actually change both signs. So really, now I have -1 times x minus 5, all of that being squared. But if I square this, -1 squared is just +1. So this leaves me with just x minus 5 squared. Okay, because I want that to look like my original problem. Okay, so now I've rewritten my negative x plus 5 squared into just x minus 5 squared. And then I can factor out a negative 1 on top to make this look like x minus 5 squared plus y squared all over y squared. Duh, I just realized I forgot to multiply the bottom by the y. This is supposed to be a y cubed on the bottom. Alright. It's been a long day. Okay, so continuing on. So now I also have the top part where it's looking like the original problem. So if I have that, then I can plug in the 36 that it was equal to. So my final second derivative is negative 36 over y cubed. Ah, thank goodness. All right. Okay, so the last part of this section is called logarithmic differentiation. We talked a little bit about this already. So basically, if you come across a super complicated looking equation, to help us find a derivative easier, we can actually use logs. Because if you remember, the derivative of a log is just 1 over x, or a natural log specifically is just 1 over x. So that makes things a lot easier to deal with, and if you remember all your log properties, then it's easy to rewrite things using log properties and make it look a lot simpler. So that's the goal. Let's say we start off with the equation y equals x minus 2 squared over the square root of x squared plus 1. So if we were to do this using like regular derivatives, we'd have quotient rule involved, we have stuff inside parentheses, so chain rules involved. It's just not the funnest. So with logarithmic differentiation, what we're basically doing is we're going to just randomly add in a log on both sides, specifically a natural log. Because if we have natural logs involved, then on the right side, I can actually rewrite this entire equation using more logs. So remember the log property where if it's being divided, you can actually rewrite them as multiple logs being subtracted. So I can split this up into log of x minus 2 squared minus log of the square root of x squared plus 1. Okay, it's looking better already because now I know I don't need quotient rule. And then remember, exponents can also be rewritten so that you can bring the exponent down to the front. So natural log of x minus 2 squared is just 2 times the natural log of x minus 2. And once it's like being multiplied by that 2 instead of being squared, then it's just a constant multiplier now. So when we find the derivative, the 2 just stays there. Easier. And then on the square root of x squared plus 1, remember square roots are really just an exponent of 1/2. So I can rewrite this, since it's an exponent of 1/2, I can bring that down to the front. So this is just 1/2 times natural log of x squared plus 1. And so it looks a lot nicer that way. On the other side, we still have natural log of y. Okay, so now we're just going to find the derivative of both sides. On the left, the natural log of y, the derivative is going to be 1 over y times y prime. So remember, with implicit differentiation, anytime you're taking the derivative of something that's not x, you need the prime. So 1 over y times y prime. On the other side, I've got 2 natural log of x minus 2. I'll deal with that first. This does require chain rule because I've got something on the inside of a parentheses. So my inside is going to be x minus 2. The outside would be the 2 natural log of stuff in the parentheses. So the derivative of the outside would be 2 times 1 over the stuff, which is x minus 2, times the derivative of the inside. And since the inside was just x minus 2, the derivative is just 1. Minus, again, we need chain rule because we've got the inside is x squared plus 1. The outside would be 1/2 times the natural log of stuff. So the derivative of the outside is going to be 1/2 times 1 over the stuff, which is x squared plus 1, times the derivative of the inside. So x squared plus 1, the derivative is 2x. Okay, I'm just going to multiply stuff out and simplify it a little bit. So I end up with 1 over y times y prime is 2 over x minus 2 minus x over x squared plus 1. And so remember, our goal is to get y prime by itself because we're finding the derivative. So I'm going to multiply both sides by y. That way I get y prime by itself. And y, if we think back to the original problem, was x minus 2 squared over the square root of x squared plus 1. So I'm actually going to plug that in for y. So simplifying this out, I'm going to distribute my y into both of the fractions that I had. So this will end up being 2 times x minus 2 squared over x minus 2 times, and I'm going to rewrite the radical as an exponent. So x squared plus 1 raised to the 1/2 power minus, and then distributing to the other fraction, I have x times x minus 2 squared over x squared plus 1 times x squared plus 1 to the 1/2 power. But wait, I can simplify that more because x squared plus 1 times x squared plus 1 to the 1/2 power, they have the same base, so I can just add the exponents. So the x squared plus 1 really has an exponent of 1. I can add that to the 1/2 to get me x squared plus 1 raised to the 3 over 2 power. And with my first fraction, I have an x minus 2 on top and on bottom, so one of these should cancel out. So getting rid of the square, basically. So I'm going to end up with 2 times x minus 2 over x squared plus 1 to the 1/2. And so to fully simplify, we just need to combine our two fractions together, so I just need common denominators. If I multiply the first fraction by another x squared plus 1 on both the top and the bottom, that'll make my denominator the same as my second fraction now. So this will end up being x squared plus 1 raised to the 1/2 power for both fractions. From here, I just need to simplify the top. So because I have common denominators already, I can simplify everything on top and combine like terms once I have everything distributed out. So 2 times x minus 2 times x squared plus 1, I can distribute and then FOIL. And then I'm going to FOIL out my x minus 2 squared first before I multiply by the x. And then lastly, of course, we need to distribute our negative signs. So we're going to end up with 2x cubed minus 4x squared plus 2x minus 4 minus x cubed plus 4x squared minus 4x. And combining all our like terms together, we're going to end up with x cubed minus 2x minus 4 over x squared plus 1 raised to the 3 over 2 power. So with logarithmic differentiation, I can't say that it's like a shorter of a problem. It's not quite a shortcut, but it does eliminate the need for both quotient and chain rule by kind of simplifying things out with natural logs instead. For this problem, most of like the length of it came from actually just having to simplify and like make common denominators, stuff like that, which is something you would have had to do anyways with the quotient rule and chain rule. So yeah, to me it's slightly easier. Alrighty, that's all I got for this section. This concludes 2.5. Thanks for watching. Bye.